So we're going to do the energy socrative questions in this video. So how it's going to work is we're going to be going back and forth between me reading them on the computer and then explaining the answer on the front board here. So I've always wanted to kind of say this, so timestamps below. Let's get right into it. Like and subscribe.
Newton's I hat, 4 newtons J hat acts on a body as it moves from point P, which is at 2,6, to point Q, 14,1. How much work is done by the force?
All right, let's take a look at number 1. So we are looking for work. Work is force dot displacement, a straight line displacement. So since they gave us components, we're going to have to do it in component form. Now, in order to find out the x displacement and the y displacement, we have to look at those initial and final positions. So on my way from 2 to 14, I added 12 to my x direction, and on my way from 6 back to 1, I had a -5. So putting that into my work function, I get a 16 joules.
Correct answer? A. Good job. Next one. A stopper on a string is whirled in a circle. The tension in the string does work. True or false?
All right, the answer is false here because our tension is pointing perpendicular to our velocity or our displacement in that small sense. And so since force is perpendicular to displacement, work is 0, so the tension does no work. False.
Correct answer? False. If a constant non-zero net force acts on a particle, which of the following could remain constant?
All right, so this one asks us if I have a constant non-zero net force, what's going to stay constant? Well, if I have a net force that's constant and I have a constant mass, which is very common, I will have a constant acceleration. Now, some people might think, well, what about speed? Because if I have a constant tension in that string as I whirl around that stopper, I'm going to have a constant speed if I have a constant radius. Now, the problem here is this is not a constant non-zero force because it's only constant in magnitude. That force is always changing. Okay, there you go.
Correct. Acceleration. Number 4. When a force F is applied to an ideal spring, the spring stretches a distance x from its unstretched length and does work W. If instead a force of 2F is applied, then what distance is the spring stretched in terms of x, and how much work is done in terms of W?
All right, so we're looking at what happens if we double the force applied to a spring. What happens to the displacement and what happens to the work? So if I double the force, I will have to double the amount it is stretched. If I double the amount it is stretched, 2 squared, that's going to require 4 times the amount of work in order to make that happen. Correct answer here, C.
Yes, C. 2 times the x, 4 times the work. Number 5. If work is required to stretch a spring a distance x from the equilibrium position, then what amount of work in terms of W is required to stretch the spring 3x?
Similar to the last one here, so if we triple the distance, that's going to be 9 times the work. Correct answer there, D.
Correct, 9W, so D. Number 6, an elevator is hoisted by cables at a constant speed. The net work done on the elevator is?
All right, so the key word in here for our elevator is constant speed. Constant speed means our change in kinetic energy is 0, and that means our work net is 0 because work net is equal to change in kinetic energy. So the correct answer here is C.
Correct answer, 0 there. A tractor driving on a level road at a constant speed pulls a sled loaded with firewood. There is friction between the sled and the road. The total work done on the sled after it has moved a distance D is?
So the key word here is constant speed. So the tractor is moving at a constant speed, so is the sled. Therefore, the change in kinetic energy is 0. Therefore, the work net is 0 because work net is equal to change in kinetic energy. Correct answer, C. Kind of had a little deja vu from the last one there, huh?
Yes, 0, that constant speed, yeah. A non-zero net force acts on an object. Which of the following quantities could be constant?
All right, so a little tricky here. So if I think about a net force, I can have the speed stay constant because all I'm doing is changing the direction of the velocity, in which case my kinetic energy will stay constant. So it could do that. It doesn't have to, but there's no way to keep the velocity constant if I have a net force, because that means there is a change in the acceleration. So the only correct answer here is A.
Yes, A only. The kinetic energy of a car increases more when speeding up from 10 to 15, 15 to 20, or they are the same.
All right, so let's look at change in kinetic energy. So change in kinetic energy, we can rewrite this a little bit, and it's really about how are the change in those speeds squared. And so I'll note that 20 squared minus 15 squared is going to be greater than 15 squared minus 10 squared. So it's going to take a lot more energy to increase at those higher speeds. If I graph kinetic energy versus speed, and I say, okay, I'm going from 10 to 15, then I'm going from 15 to 20, I'll see that that jump gets bigger and bigger with each incremental amount I need. And so the idea is the amount of energy you need for big jumps gets bigger and bigger. So trying to launch a rocket, trying to get something going very, very fast, like, yeah, it's easy for us to get like a car going, but to get a rocket going, okay, we need to go way up here. We're going to need more and more kinetic energy. That's also why, like, if you just slam on the gas in your car and you just go, like, eventually your car can't speed up anymore, because that energy requirement for that next increment of speed is so large, it takes your engine a long time to produce that much energy. There you go. Correct answer here again, B.
Yes, from 15 to 20, B. An elevator is being lifted at a constant speed by a steel cable attached to an elevator electric motor. Which statement is correct?
All right, this one's asking, is the work positive or negative? So we'll remember if the force and displacement are in the same direction, we have positive work, so we have positive work done by the cable. If the force and displacement are in opposite directions, we have negative work, so gravity's doing negative work as it is hoisting it up. Correct answer, B.
Correct. The cable does positive work, gravity does negative work. Number 11, a piece of fruit falls straight down as it falls. Tell me about the gravitational forces doing work and their potential energy changes.
All right, let's take a look. So as this fruit falls, I'll note that the force and the displacement are in the same direction, which makes the work positive, of course. Also, another thing to note, if I have positive work, that means energy is going from my potential energy to my kinetic energy. So whenever we have positive work, we have a loss of our potential energy. So we're going to do positive work, and we're going to have a negative change in the potential energy. Correct answer, B.
Correct answer is B. The force does positive work and the potential energy decreases. Number 12, if the potential energy is stored in a spring is stretched a distance x from its equilibrium, then how much potential energy is stored when the spring is stretched a distance of 3 times that?
All right, let's take a look at this. So if we do 3 times the x, it's going to be 3 squared, so it's 9 times the potential energy stored there. So the correct answer, D.
Correct. 9 times the potential energy is stored. Each object is released from rest and experiences no friction or air resistance. In which case, if any, will the mass have the greatest speed at the bottom? And here are those 3 options.
All right, let's take a look at number 13 here. So all of them start at one point, go to another point. So we're going to use the work kinetic energy theorem, where we find out that the speed is equal to square root of 2gh. What that means is that if they all have the same height, they're all going to have the same speed at the bottom. Now, mass cancels out, so mass doesn't matter. So what about the angles? The angles don't make a difference in the final speed. What they will make a difference on is the acceleration and the time it takes, but in the end, our speeds will be the same. So the correct answer is D.
Correct answer, they have all the same speed. Number 14, each object is released from rest and experiences no friction or air resistance. In which case, if any, does gravity do more work?
All All right, so 14, we're looking at the work done by gravity, which is going to be that mgh. As it falls, it's going to have a positive, well, they're both going to be negative, so it's going to make it positive. So we're going to do a positive work. So the one with the largest mass, because they're all falling the same height, is going to do the most work. So the 2m is going to do the most work. Correct answer there, C.
Correct answer, C, because it has double that mass. A brick is dropped from the top of a building through air. Friction is present to the ground below. How much work does the brick, or how does the brick's kinetic energy just before striking the ground compare with the gravitational potential energy U at the top of the building? Set y equals 0 at ground level.
All right, let's take a look at 15. So as that ball falls, or that object falls, it starts with gravitational potential energy and no kinetic energy. As it falls, it loses that gravitational potential energy and it gains kinetic energy. We're thinking about that gravity doing work to transfer from potential energy to kinetic energy. However, along the way, there is some work done by friction, which siphons off some of that energy. And so it's going to maybe do -1 joule of work. And in doing so, 10 and -1 turns out to be left with only 9 joules left of kinetic energy. So as that energy is transferred over, some of that energy is lost to friction. So not all of it makes it over there. So the correct answer here is C.
Kinetic energy is less because we lose some of that potential energy to friction on the way down. The two ramps shown are both frictionless, and heights y1 and y2 are the same for each ramp. A block of mass m is released from rest at the left-hand end of each ramp. Which block arrives at the right-hand end with a greater speed? Here are two.
All right, so in this one, again, we're going from one point to another point, so very similar to, I believe it was number 13. So when we look at that change from potential energy to kinetic energy, we find the speed is equal to square root of 2gh. So since they have the same height, they have the same v. They take different paths, so they're going to have different accelerations, they're going to have different times, they're going to have different velocities along that path, but in the end, they're going to have the same speed.
Correct answer, they have the same speed. Now they will get there in different times, but they will have the same speed. Consider two frictionless inclined planes with the same vertical height. Plane A makes an angle of 30 degrees with the horizontal, so A would be on the right here. And plane B makes an angle of 60 degrees with the horizontal. Mass M1 is placed at the top of plane 1 and M2 at the top of plane 2. Both masses are released at the same time. At the bottom, which mass is going faster?
Same concept. So if we look at that kinetic energy theorem, we see that the speed is equal to square root of 2gh. So since they have the same height, they have the same speed at the bottom. Again, acceleration and time will be different, but they will have the same speed at the bottom. Correct answer, C.
Correct, they have the same speed. 18, you toss a 0.15 kilogram ball straight upward so it leaves your hand moving at 20 meters per second. The ball reaches a maximum height of y2. What is the speed of the ball when it is at a height of y2 over 2? So at half that height, you can ignore air resistance.
All right, let's take a look at this one. So we have this ball, it starts here and it goes up and it ends here. So at the top, all of the energy is in the form of potential energy. There's no kinetic energy. So I'm at mgh at the top. That's the total amount of energy. So at half the height, well then I'm at mgh over 2. So half the height is going to give me half the potential energy. So what that means is half of that total energy is in kinetic and half is in potential at this point. So if I go to kinetic energy now and I say kinetic energy is 1/2 mv squared, and I say, all right, I want half of the kinetic energy, what do I need to multiply v by here? Okay, so something squared is going to be a half, so 1 over the square root of 2. Or if you're, one of those math people, the square root of 2 over 2 works as well. So I have 1 over the square root of 2. So all I need to do is then just take my number, the 20, divided by the square root of 2 to find that my speed is correct answer here, greater than 10 and C. There you go.
Correct, it is greater than 10. A block is released from rest on a frictionless incline as shown. When the moving block is in contact with the spring and compressing it, what is happening to the gravitational potential energy, UG, and the elastic potential energy, UEL?
All right, so as this block goes down here, it's going to be increasing the amount the spring is stretched, which increases the amount of elastic potential energy stored. As the block goes down, the height is going to be decreasing, and so I'm going to be decreasing the amount of gravitational potential energy that's stored. So we're losing gravitational potential energy and gaining elastic potential energy. So the correct answer there is D.
Correct. UG is decreasing, UEL is increasing. Number 20. Two objects with different masses have gravitational potential energy of 100 joules on Earth. They are released from rest and fall to the ground. Which of the following statements is true?
All right, so since they both start with the same amount of potential energy at the top, say 100 joules, all of that 100 joules gets to turn into kinetic energy, so they will have the same at the bottom. Now, if they have different masses, they're going to start at different heights. If they start at different heights, they're going to take different times to reach the ground. They're also going to reach the ground with different speeds, much the same as if they have the same kinetic energy at the bottom but different masses, they're going to have different speeds. So they will have the same potential and kinetic energy at the start and end though. So B is our correct answer.
Correct. They will have the same kinetic energy when they reach the ground. Good. 21. You push a block on a level surface at a constant speed. There is friction between the block and the floor. The rate at which the energy is removed by friction is?
All right, the key word here is constant speed. So that means our work net is going to be 0. So that means that when I add the work in and the work done by friction together, I'm going to get 0. I'm going to get a constant speed, meaning we have equal and opposite works there. So correct answer, B.
The same as the rate at which we do work. So all that work you're putting in gets taken right back out by friction. You push a block up an incline at a constant speed. There is friction between the block and the ramp. The rate at which energy is removed by friction is?
All right, again, we have constant speed here, so the net work is 0, but we do have an incline, so gravity's going to be doing some work in there too, so we're going to be moving in some potential energy. So when I think about my work kinetic energy theorem, I have work in, I have work done by friction, but now it's not going to be equal to 0, so they're not going to be equal and opposite. So I got to start with more work in than friction takes out, so that in the end I'm left with an increase in gravitational potential energy, and we go up. Correct answer here is C.
Less than the rate at which you do work on the block, because some of your work has to go into increasing the potential energy of that block. You slam on the brakes of your car in a panic and skid a distance D on a straight and level road. If you had been traveling twice as fast, what distance would the car have skidded under the same conditions?
Okay, so let's take a look here. So we're skidding to a halt, and so it says, what if I'm going twice as fast? What happens to the displacement? So if I'm going twice as fast, that's 2 squared. That means it's going to take 4 times the distance to come to a stop, and that is not including the distance you travel while you're reacting. So if you're moving faster, you're also traveling a further distance while you react. So that distance is actually larger. That's why in a school zone, instead of going 30 miles an hour, a little bit over the speed limit, you're supposed to pull it back to 15. Half that speed is going to be a quarter that distance. You're going to stop faster. You're also not going to travel as far while you're reacting. So good idea there. Correct answer, A.
D, correct. A, correct. 4 times that distance. You wish to accelerate your car from rest at a constant acceleration. Assume that there is negligible air drag. To create a constant acceleration, your car's engine must?
All right, let's keep that constant acceleration. So in order to figure out the power is equal to the force delivered times the velocity at which it's going at, dot product to be specific. And that force is going to cause your car to accelerate, so an MA. Now if A is going to stay constant, But as I accelerate, my velocity goes up. My power must also go up in order to keep that acceleration constant. If my power is constant, well, as my velocity goes up, my acceleration goes down. We see this in our car. If you try to speed up, the faster you go, the slower your acceleration is, just because your car can't deliver energy at a fast enough rate to maintain that acceleration.
C, develop an ever-increasing power. The graph shows the potential energy U of a particle that moves along the x-axis. The particle is initially at x equals d and moves in the negative x direction. At which of the labeled coordinates does the particle have the greatest speed?
All right, so we're looking at our potential energy function. Let's put some bounds on that. So we're looking at our potential energy function, and we want to know when we have a maximum kinetic energy. So because the kinetic energy plus the potential energy equals the total amount of energy, whenever we reach a situation where the potential energy is a minimum, the kinetic energy is going to be a maximum. And so I'm looking for where is potential energy the lowest, and it's the lowest at B. And there you go. Oh, there is another way to do this, remember. Like, you can flip this graph and then it becomes a kinetic energy graph. So if I was to just flip this, invert it, vertically, I will see that this is a maximum point. So if I was to take my paper and just flip it around here, I could see that this is a maximum point for kinetic energy, because that would be your kinetic energy graph then.
Correct. It will have the greatest speed at that location of the highest kinetic energy, so at B. 26, a graph shows the potential energy of a particle that moves along the x-axis. The particle is initially at x equals d and moves in the negative x direction. At which of the labeled x coordinates is the particle slowing down?
All right, 26. So our particle is moving this direction. And when it's moving this direction, in order to have a slowing down, I have to have a positive force. So I have a negative velocity. Positive force is going to give me a slowing down scenario. So to look for the force, I'm going to have to take the negative derivative of our potential energy. In other words, I need to flip the sign on the slope. So in order to have a positive force, I need to have a negative slope. So where along this path does it have a negative slope? Well, here it has a positive slope, zero slope, negative slope. So at A. The other way to think about this is you can imagine just putting a marble on there and letting it roll. Where is it going to be slowing down in that scenario? So on this way, as it starts moving this way, it's going to be speeding up, speeding up, speeding up, and then it starts to slow down, slow down, slow down. Now, if it was moving the other direction on the way back, now it's going to be speeding up at A and slowing down at C. So that information about what direction was it moving was very helpful for us to figure out that answer to be A.
Correct. At x equals A, it is slowing down. The graph shows the potential energy U for a particle that moves along the x-axis. At which of the labeled coordinates is there a zero force on the particle?
All right, so 27 wants to know where is the force zero. So the force is equal to the negative derivative of the potential energy function with respect to x. So wherever my derivative is zero, so that would be at B and D.
Yep, at B and D, you're looking for where is that slope zero. 28, the graph shows a conservative force, f of x, as a function of x in the vicinity of x equals a. As the graph shows, f of x equals 0 at x equals a, which statement is, or about the potential energy function u at x equals a, is correct?
All right, so let's take a look. So what we're given to start with is a force graph, and we're asked about what the potential energy is. So remembering that the negative derivative of the potential energy gives us the force function, to go backwards, I need to take the negative integral. So if I have a linear force function like this, and it has a positive slope, it's going to have some intercept that's negative, who cares? But I'll see that my potential energy is a negative x squared. So I should end up with some sort of parabola that is curved down. So I'll note here that the force is a negative value, which means that the slope is a positive value, because the negatives will cancel out, so my slope better be positive. And I should have a scenario like this. At this point, my slope is 0, because my force is 0. On this side, my force is positive. which means my slope has to be negative so that those two negatives cancel out. And so I get this. So that means at point A, we have a maximum in the potential energy. Correct answer is B. There is no quick way to do this in your head. This negative messes with people. So just take it slow and think about, okay, during this region, what's the slope going to be? Well, if the force is negative, the slope is positive. Over here, the force is positive, so the slope is negative. Obviously, I have a maximum then. Okay?
Yes, the potential energy is a maximum at that point. You really need to see what that potential energy function looks like. All right, so we have that same graph as in the last one. We want to know, what is the potential energy like at A? So they've just flipped the slope a little bit here on us.
All right, kind of the same idea here for number 29. So I noticed that my force function has a negative linear line, so that my force function will have a negative x type term, plus some intercept, plus some slope value. That means my potential energy function integrating with a negative integral will give me a concave up parabola of some degree. So I should get some sort of parabola like this. The other way to think about that is that I have a positive force here. That means I have to have a negative slope. And then over here I have a negative force, so I need a positive slope. And at A it's got to be 0. So I end up with this minimum in my potential energy function. Correct answer, C.
Correct. Now it's at a minimum. And again, you really got to create that potential energy function. All right, we have another graph of potential or force versus position. We want to know what's true about the potential energy at A.
All right, so we have this slope. Again, it doesn't cross the inner or cross our axis though, so I haven't reached the force equals 0 point. I have a negative linear function, so I'm going to end up with a positive, and so I'm going to have a concave up. But you'll see that my point where it's going to cross that axis is going to be to the right. So I'm just going to have like that left half of the parabola there. The other way to look at this is, all right, the force starts out big and positive. That means the slope has to be big and negative. And it gets smaller and smaller. So I end up with a smaller and smaller negative slope. So what that is going to look like is it's going to be steep at the start. And it's going to kind of trail off like this. Now the idea is at some point in the future it's going to cross 0. At some point in the future it's going to bottom out. We don't know when that is, of course, but correct answer there is B.
Correct. That potential energy at A is a less than 0 is the slope at A.